Okay, let's review this. So number 3, we're trying to find how much the capacitance changed. What do I do? Okay, I understand. So we started out 0.5 meters away, or centimeters, I guess. It doesn't really say that in the problem. And then it's separated by 1 centimeter. So we double the distance, which according to my capacitance equation, which is for a parallel, this is only true for a parallel plate capacitor. Please don't do this for other capacitors. Only true for a parallel plate. If you double the distance, the capacitance drops in half. Drops in half. Okay. Because capacitance and distance are inversely related. Now what about the potential? So it's connected to a battery, right? Oh, it's disconnected. Okay, that's good to know. Since it's disconnected to the battery, that means the charge does not change. Q does not change. Okay? And so if we look at my capacitance equation, charge over the potential difference, the capacitance, the charge did not change. The capacitance dropped in half, which means that the potential difference doubled. It's the only way for that to happen. Conceptually, we can kind of understand why. We're farther away, and it's still the same charge, still the same electric field between the plates. Remember, the electric field for a parallel plate capacitor is constant. So there's electric field between these plates from positive to negative in this way. And when we double the distance, the electric field's even longer, right? It acts for a longer time. So you can imagine if I place a charge here, it's going to accelerate towards this plate and reach some speed. But if I were to place a charge here, it would accelerate for even more time until it reaches an even greater speed when it hits this plate. So that tells us that the potential difference is greater. There's more energy in the system. In fact, the next question is energy. So let's use my energy equation. I'm not sure which one it is. So I'm just going to write out the first one that's in the equation sheet, 1/2 Q delta V. Yeah, this will be it. So Q is the same, delta V doubled, so that means that the energy doubled as well. Energy doubled as well. And so where did this energy come from? It came from your hands. So there's more energy in the system from your hands separating the plates. Separating plates. The plates don't want to be separated. Again, we have a positive plate and a negative plate, a positive plate and a negative plate. Opposites attract, so they want to be close together. So separating them, you have to do work to the system, add work to the system. You increase the amount of energy. Okay. Okay, so we have energy, so UC. We have a distance, D. We have a charge, Q. And we're trying to find the potential difference. So I'm just going to use my this equation. So UC is 1/2 Q delta V. Or if I solve for delta V, I get delta V is equal to 2 UC over Q. Okay. And so that's 6.2 times 10 to the minus 4th. Q is 8 points times 2, and then Q is 8.6 times 10 to the minus 6th. And pardon me while I use my calculator. Let me pause the video so you don't have to wait for me. Okay, I'm back. So this potential difference is 144 volts, 0.2 volts, something like that. Okay. Now what's the capacitance of the capacitor? So I'll probably just use this. So C is Q over delta V. Q in this case is this number. 8.6 times 10 to the minus 6th. And delta V is 144.2. And so according to my calculator, this is going to be a number. I got 5.96 times 10 to the minus 8th farads, which seems reasonable. Okay, now that's why I want to do this problem. I'm wondering why I did this problem. At what speed? This is an energy problem. If you ever see this, the potential energy, the change in potential energy, is equal to, some students are going to enter, is equal to kinetic energy. Now the potential energy we're going to use is not the energy stored in the capacitor. No. It's this one. potential difference times the charge of a proton. This is the energy equation that we're going to use, Q delta V. So Q delta V is equal to 1/2 mv squared, or if you solve for V, you get V is equal to root 2Q delta V over M. And I'm just going to plug in all the numbers. So 2 is 2, Q is 8.6 times 10 to the minus 6. Delta V is a number, 144.2. And then the mass is the mass of a proton, which I don't memorize, but the equation sheet has it. That's a proton, right? Yeah, mass of a proton, 1.67 times 10 to the minus 27. And let me get my calculator and bust out an answer. So I'm going to pause the video. And I just realized my mistake. This Q is wrong. This should be the charge of a proton, not the charge stored on the plate, charge of a proton. And so the charge of a proton.
That's the issue with suicide on all the same letters.
Yeah.
Actually, this Q is a different Q.
1.67 times 10 to minus 27. So this is 1.67 times 10 to minus 27. Let me pause the video and I will come back to you. And I made another mistake, which I just realized. So the Q is the charge of a proton, which is this. I got that wrong. And then this is the mass of the proton. And so when you get an answer, students are entering. So I'm going to stop the video right now, meters for every second. So that's my answer. Wow, that took a long time. Now an electron has less mass. So less mass, greater velocity.
How are you today? Good.
According to this equation. Electron has a lot less mass. Same charge, but less mass. So much less velocity. Let's pause the video. Okay, onwards. 5 and 6 actually are duplicated of previous questions that I've asked. I'm not going to do those. So I told you to skip them. Hopefully you saw the Canvas announcement. But let's do 7 and 8, and then we'll be done. So we're going to find the equivalent capacitance of this mess. No one draws circuit diagrams like this, and so no one does it. So I'm just going to label these capacitors, and we're going to redraw this circuit to something that actually makes sense to me. I see that these are in series, but I'm just going to redraw it. So we have the battery, that's the battery, and then this line goes up, and then it splits into two pieces. So the line goes up, and we split into two pieces, okay? And then we hit capacitor 1, and then we hit capacitor 2, and then we go, let's move that thing, we go all the way back to our battery, right? So we hit capacitor 1, we hit capacitor 2, and then we go all the way back to our battery. And point A is right here in between 1 and 2. Now let's focus on this split. So this splits, and it splits into 2 again. So here it is, and then it splits into 2 again. Okay? And then we hit capacitor 3, and then capacitor 4, and we're back home. So capacitor 3, capacitor 4, and then we're back home. We hit capacitor 5 and 6, and we're back home. And we're back home. And then point B is right here between these two spots, point B. So this, to me, looks like a parallel circuit. I can even redraw it even a little bit better than this. A parallel circuit with 3 different branches. Okay? And each branch has 2 capacitors. So, boom. So 1, 2, 3, 4, 5, and 6. And this is point A, and this is point B. So once I redraw it like this, I think it's easier to find the equivalent capacitance. So let's call this capacitance of C, and this is a capacitance of C. When you add up these two, these are in series. So remember, equivalent capacitance in series is equal to 1 over C1 plus 1 over C2 inverse. And if they're both C, it's 1 over C plus 1 over C, which is 2 over C, and then you inverse that. So the equivalent capacitance of this thing is C over 2, half the capacitance. Same thing here, half the capacitance, same thing here, half the capacitance. So this circuit is very similar to this circuit. We have 3 capacitors all in parallel, and each of them have a capacitance of C over 2. So all of them have a capacitance of C over 2. And they're all in parallel, which makes this problem really easy. So to find the equivalent capacitance in parallel, all we have to do is add C over 2 plus C over 2 plus C over 2 is 3C over 2. Pretty sure that's it. I was looking at this, I had no idea how to find the voltage potential difference between point A and B. I was like, I don't know. But I think once we redraw it like this, I can see. I'm pretty sure it's 0. Okay. And I think you can see why. So let's imagine this is a 12-volt battery. Okay. Each of these branches, these are parallel branches. Let's imagine this is a 12-volt battery. We saw in parallel that the potential difference across each branch is also 12 volts, 12 volts, 12 volts. So that's the same here. Across these 2 points, 12 volts. Across these 2 points, 12 volts. Across these 2 points, 12 volts. So now let's just focus on this one part. 12 volts to 0 volts. That's how much our potential dropped. We have a 12-volt difference. If these capacitors are identical, each capacitor is going to get a 6-volt drop. Because in series, the potential differences add up to equal the battery. So this is 12 volts to 6 volts to 0 volts. That's how our potential dropped. Same thing happened here, from 12 volts to 6 volts to 0 volts. Both of these are at 6 volts of potential. They're both at the same potential of 6 volts, so their potential difference is 0 volts. Pretty sure that's right. Nasty problem. Sorry about that. Number 8's also kind of crazy. So when we turn it to switch A, we need to find how much charge is stored in this capacitor. And so we get that capacitance is Q over delta V, or that charge, I'm going to call this the charge on 1, is equal to C delta V. So Q1 is equal to C, which is 15 microfarads, times 10 to the minus 6th, times 100, which is the voltage. And so Q1 is going to be equal to 15 times 10 to the minus 4 coulombs of charge. Okay, so that's Q1. Nowhere does the problem ask me to do that. Okay. And then once the switch is closed here, and the potential difference is 100 volts, so that's something to keep in mind as well. Once the switch is closed here, this charge is not going to leave. This charge is going to remain in the circuit, and it's going to be distributed between these 3 capacitors. I'm going to pause the video. Okay, so let's try to keep going. So now let's imagine we flip the switch, and all we're focusing on are these 3 capacitors here. And to be honest, I don't really know how to deal with this. I'm going to put this into one capacitor. I'm going to create an equivalent capacitance where we have C1, and we have this equivalent capacitance of C23. Let's call it C23, the equivalent capacitance of both of them. I can find the capacitance of this pretty easily. These look to be in series, one right after the other. So C23, 1 over 20 plus 1 over 30 is 5 over 60, and then you flip that, that's 12 microfarads. Okay. And we know C1 is 15 microfarads. Okay. And now is this circuit, this equivalent one that we're looking at, is this series or parallel? When we only have like 2 things hooked up, you can make an argument for both, series or parallel. And it turns out it doesn't really matter which way you think about it. You should be able to get the same answer. So let's just try to see what we got. So let's call this the original charge on the circuit, Q1 naught or whatever, Q1 0. Now we want to find the new charge. The charge that was originally here, some of it's going to leave and again be deposited on these other plates. So the new Q1 is going to be less than Q naught. This is the maximum charge that's going to be in the total circuit, the amount of charge total. So we're going to write an expression that Q1 naught, this 15 times 10 to the negative 4th, is equal to the new Q1 plus this Q23, the equivalent charge stored. Okay. What else do we know? We need another equation. Let's do potential difference. It turns out if like I look at points A and B, I call this point A, point, I don't know, alpha and point Bravo or whatever. The potential difference across both has to be the same. Has to be, sorry, we can see that the potential difference across 1 is actually going to be equal to the potential difference across the combined capacitors 2 and 3 because they both share these points, alpha and Bravo. The potential only changes at capacitors, not wires. Another way to think about it is that the potential differences have to be the same, otherwise charge would move. And right now we're in a static place, charge has already moved. So we're set up static-wise. So let's use my definition of capacitance. So what is my definition of capacitance? C is Q over delta V. or delta V is Q over C. And let's throw that in here. So delta V1 is Q1, the new Q1, over C1. Okay. And delta V23 is Q23 over C23. We know what C23 is at 12 microfarads. We know what C1 is at 15. These are two unknowns, but I had this other equation where I know that Q1 is equal to Q1 naught, this 15 times 10 to the minus fourth, minus Q23. So what I'm going to do is I'm going to take this equation and plug this in. So instead of Q1, I'm going to write this as Q1 1 naught minus Q23 over C1 is equal to Q23 over C23. I'm starting to regret assigning you this problem because this problem is absolutely nasty, absolutely filthy. So sorry about that. This is probably the hardest problem I've assigned all year. I'm going to do some algebra. I'm going to solve for Q23. I'm going to pause the video. You don't have to watch it. Okay, so here's my algebra solving for C23. I just cross multiplied and then solved for Q23. And these are all known, so I just plugged in the numbers. And when you do this, you get Q23. Wow, this is an absolute mess. So pause the video. You get Q23 is equal to 5.55 times 10 to the minus fourth coulombs, okay? And that gives me Q1, because Q1 is Q10 minus Q23. So Q1 is Q10, which is 15 times 10 to the negative fourth, minus 5.5 times 10 to the minus fourth. And so that gives me Q1 is equal to something times 10 to the minus fourth. It should be a 9 or something. 15. Uh, 9.44 times 10 to the minus fourth coulombs. So that gives me Q1. I finally got one of my answers. That was just one of the 6 things I asked you to find. That also gives me the potential difference, because potential difference is Q over C. So the potential difference across 1 is Q1 over C1. Okay. So 9.44 divided by this 15 to the minus 6th power, and you get 62.96 volts. Okay. So that got me one thing. I got Q1 and delta V1. Now we can deal with this part, this side. So I need another piece of paper, of course, because I didn't give you nearly enough room for this. Whatever, I'll just go here. Okay. So again, my circuit is here. Oh, do I have to go? No. My circuit is here. And I know the potential difference across these 2 points, I just found it, is 62.96 volts. Remember, the potential difference has to be the same. Okay. So I know the potential difference across this from B to A. This potential difference is 62.96. Boop. And I can find the charge. Did I already find that? I did find the charge stored in 2,3. Okay, that's not very helpful. How do I go from here? What do I do next? Pause the video while I think about this. Okay, I'm back. I took a little walk. I knew I made a mistake. I figured it out after walking. I just mismultiplied in my calculator. This times this divided by this is 6.67 times 10 to the minus fourth, not the 5.55 that I originally had. So that's the equivalent charge on the equivalent plates. And that gets me Q1, because remember Q1, which is what I want to find, is equal to the original Q1 minus the Q23, because that original charge is distributed to both new capacitors. And so when I take 15 times 10 to the negative fourth, the original charge stored in the capacitor, and subtract this new charge, the 6.66 times 10 to the minus fourth, I get a number 8.33 times 10 to the minus fourth, 8.33. And that gets me a new voltage, because again, the voltage difference across the first capacitor is Q1, 8.33 times 10 to the minus fourth, divided by C1, which is 15 microfarads, When I divide those, I get 55.55 volts. Whew. Now I can work on the second side with a piece of paper that I brought and promptly lost. Okay, so now I can work on this side. So essentially, I have here two capacitors, a 20 microfarad and a 30 microfarad. And I know the charge in each of them, so the charge in 20 is equal to the charge in 30, and it's also equal to the charge of the equivalent capacitance, the 2030, the 2,3, because these are in series. And so I know Q23, I already solved for it previously. I pray that I wrote it down. Yes, I did. The 6.66 times 10 to the minus fourth. 6.66 times 10 to the minus fourth coulombs. Okay. And so that's equal to Q20. So Q20 is 6.66 times 10 to the minus fourth. And Q30 is also 6.66 times 10 to the minus fourth coulombs. Minus fourth coulombs. So now I just need to find the voltages and I'm done. So the voltages are pretty easy. So the voltage difference, I don't remember the equation. So capacitance is Q over delta V. So the voltage difference is Q over C. So that's 6.66 times 10 to the minus fourth. For the 20 ohm capacitor, for the 20 microfarad capacitor divided by 20 microfarads. And when you do that math, you get a number of 33 and a third volts. Okay. And then for 30, again, Q over C, Q again is 6.66 times 10 to the minus fourth over 30 times 10 to the minus sixth. And that is going to be 22.22 volts. And one way to check my work is that I know that the potential difference across the first capacitor should be equal to the potential difference across the 20 plus the potential difference across the 30, because those are kind of like in series. And that works out. They both are equal to 55.5 volts. Whew, I did my math right. So I am done. That took forever. I'm so sorry for that problem. You should yell at me. Not now, though. Later. Bye.